Hey everyone, welcome back to my deep learning second tutorial. This is my step-by-step deep learning tutorial with NumPy. So in last tutorial we wrote two functions. We wrote a standard initialized parameters function and initialized parameters deep function. So in this tutorial we'll go forward and we'll write forward propagation. So at first, when we have initialized our parameters, we'll do the forward propagation module. So we'll start by implementing some basic functions that we'll use later when implementing the model. So we will complete the three functions in this order. So I'll write that first will be our linear function, second will be linear activation function, where activation will be either ReLU or Sigmoid, and the third function would be similar as second, so linear ReLU function, and this will be something similar as a loop, so linear ReLU as deep as our network is, and the last layer will be a sigmoid, so in the last layer we'll use a sigmoid. So we can write something like linear ReLU and multiplied by L-1, so it's depth of our deep neural networks. So I could write all these functions, three of them, in one block, but then it's harder to understand the code and to learn everything by step, so I will leave it so for learning purposes. And I should remind that the linear forward module is computed always vectorized. So if you remember, it is we multiplied by a plus b. So we'll implement this function where a is our, for example, if it's for our first layer, a will be our input, so our image pixels. So at first I'll write our I'll define a function, so I'll call it linear forward, and the inputs will be simple a, w, and b, as I shown just you what we'll need. And here a will be our activations from previous layers, w will be weights matrix. It's, well, if you saw my previous videos you know this, and b will be our bias vector. Next we'll write that z will be equal to numpy dot, and wa we can, okay, and we might add b. Then we'll use a cache, so it will be for our backward propagation process, so it will be simply a, w, and b. And next return z cache. So this is our linear forward function. That's quite easy. And what it will return, it will be the z as input of the activation function, so it's also called pre-activation parameter. And cache will be a Python dictionary containing our a, w, and b, stored for computing the backward pass efficiently. So let's write our another function. So another, as I mentioned before, this will be our linear activation forward function. But before writing this, we need to write our sigmoid and ReLU functions, as I used them before, so I will not explain what they do much. So for example, if I write sigmoid z, okay, larger z will be, and now it will be a little different. We'll save a cache for our back propagation purposes. So this will be 1 divided by 1 plus numpy exponential, and here will be minus z. And what we'll return is like this, a and cache. That's quite simple, and z is what will feed into the corresponding backward function. So we'll need both a and our cache in another function. So next I'll write one more, so we'll use a ReLU rectified liner unit, activation unit. So this will be a ReLU, for example, Z. And now instead of this function, ReLU is numpy maximum, we'll call, and 0.z, and cache also might go to Z, and return cache and Z, I mean activation. So for more convenience, we are going to group two functions in here, liner and activation, into one function, liner activation function. And we'll implement a function that does the liner forward step followed by an activation forward step. So here what I'll write is another function. So actually here will be a defined liner activation and forward, and here will be our, we'll call all previous, and waits, bias, and activation. So you'll understand everything in a moment, just wait a little. So for example, we'll have two functions. So if activation, for example, is equal to Sigmoid, we'll do something here, and if our activation is our uloop, we'll do something else. So here what we'll do is we call a liner forward function. So our Z and liner cache will be equal to liner forward function, and here it simply goes our previous, waits, and bias. And next I'll copy it later, and one more will be our and activation cache. There is no such. Activation cache will be equal to sigmoid of Z. So as you see, we do here multiplication. That's why I said I could join them into one block, but it's easier to understand everything when it's separated. So here we do this multiplication, we calculate Z, and then we calculate our activation, and we save everything to cache what was before calling, for example, sigmoid or liner forward function and so on. So next we should do the same with ReLU here, and instead of this will be a ReLU, and what's left is just write a cache will equal to liner cache and activation cache, just like that, and we'll return and cache. Well, if you don't understood everything, you just watch my previous tutorial series with logistic regression or with neural networks with one hidden layer, and yeah, it's quite easy to understand. If you draw everything on the paper, it's much easier and so on. And there is one more step left. So as I said, we need to have a loop. So for example, if this is our image, then we call a liner and ReLU function, and as deep as our network is, we loop this. For example, if we have a with one hidden layer, then this will be done only once. But if we have, for example, 3 hidden layers, this loop will be done 3 times, and only then it goes to last layer, liner and sigmoid, and gives output. So this should give you more convenience with it. So we'll write our code which we'll use before, and we have already previously written it. So in the code, the variable AL will be denoted as activation, and this is sometimes called I hat. So anyway, I will just write it, and this will be much easier to understand for you. And I'll define it L model forward, just like that, and here will be our X and parameters. So X will be our simply data. It's a NumPy array of shape of input size and number of examples, and parameters output of initialized d parameters function. So from this function. So what we'll do here, at first we'll create a cache free array, and here we'll write our a equal to x, and of course we need to find how many layers we have in our network. So L will be length of parameters, and we divide this by 2 because remember that our parameters has weights and bias for one layer, so we divide it by 2. And here we write a loop I showed you in a figure. So just I'll write for L, it's L not 1, keep in mind, in range from 1 to L. And here I'll write a dot previous will be equal to a to save it, and we'll implement here a function of linear ReLU. So this will be simply a, and cache will be equal to linear activation forward. I'll copy this, linear activation forward. Here will be our a previews, here will be our parameters, weights, and here will be weights of our layer, so string L, just like that, and parameters will be quite similar. Here will be our bias with L string, and of course activation will do ReLU for our layers. So just like that, and after this we'll append our cache. Append cache. Sorry, I wrote a gap here. It should be like that. And when we do this loop for our deep layers, what we do here is at the final layer we do a sigmoid. So we'll do something very similar. We copy this layer, save it here, and here we use activation as sigmoid. And now here is our last layer, so here should be L, upper L. That's it. And here we also append our caches to the last layer, and here we'll just return AL and caches. Keep in mind, not cache but caches. So we wrote our functions. This was quite fast, and I thought it might be much longer, but yeah, we can spend some time for testings. So now we can test our functions we implemented in this tutorial with random numbers to see if they work well. So I'll initialize neural network with 2 deep layers with 4 inputs and 1 output. For inputs I will use a NumPy random function as used before. Then I'll simply just call L model forward function. So layer dims will be our neural network dimensions. So as I said before, our input will be 4. Then we just use this, and last layer will be 1 sigmoid. So parameters will be initialized parameters deep, and here I'll use layer dims. as we created right now, and here will be my larger x and pi random and rand n, and here I'll just creating random numbers for input. So I'll just create 4 numbers. This is 4 inputs, I mean, to our first network. If here we'll write 5, then here also should be 5. So that's it. And here I'll just write 10. And next, what we'll need to call is al caches, and we call elf model forward. And here is our x and parameters, just like that. And what we want to see later is what we print out. So I'll just write a print, for example, and here will be my x.shape. I want to see what shape my data has, so x.shape, like that. And then I'll use print al equal to something, and here will be my al. And next I'll just print another value that will be length of cache list. So length of caches list, and here I'll just write length of caches. And next, the last is we would like to see what our parameters has. So we'll see like that in parameters. Well, you can print more results if you want, but this is my example what I would like to do. So if everything should be fine, I'll just build, and yes, we see some mistake here, and here I made a mistake. Doesn't matter, I'll fix it in a moment. And okay, let me check this out. And here should be not previous a but a, just like that. Okay, and here is our results we received, and as you can see, our shape of our input data is, for example, 4, and number of examples is 10, for example, and yl is just like this numpy array. Then our length of caches list is 3, so it means we have weights for 3 layers, so input, one hidden and another hidden layer. And here's our weights, for example, for first layer, weights for another and third. And yeah, that's quite it. And if you would like, we can write a more deeper layer network, just like that. We'll build this, and okay, and then we have weight 4 and so on. So nothing that much different. You might receive quite similar results, but they might be different a little because of random numbers we use. So that's it. Now we have full for propagation that takes the input x and outputs a row vector a containing our predictions. It also records all intermediate values in caches. So using al, we can compute the cost of our predictions. So this was a little more difficult tutorial part to understand than before, but don't worry, you can read it a few more times, print values out to get better understanding, play a little with it, and you'll understand. Don't worry, we'll write it everything later, so you'll be able to understand everything step by step, but you can try to draw it on a paper or something like that to get a better understanding. So in next tutorial, we'll build a cost function and we'll start building a backpropagation function. So actually cost will be quite similar, but backpropagation, well, you'll see this is more difficult than you think. Okay, so thank you all for watching. Subscribe my channel, like my tutorial, of course. You can read it, visit my other tutorials, learn from me, please. And yeah, I hope this tutorial will be helpful for you, and thank you all for watching. Good luck and see you in a next time.